Hello, welcome to a new video. This video is in this video we are going to discuss some concepts in fundamental groups. We will be discussing additional examples of fundamental group in some videos that follow this particular video. So first of all, we want to discuss the concept of deformation retract. So these the two concepts are here we want to discuss: deformation retraction and then deformation retract. Deformation retraction is a function, but deformation retract, it's a subspace of a given space. So the given space, here x is the given space. We consider we name the given space as x. And let D be a subspace of X. So we are given a space X and a subspace, and D is a subspace of that given space. Then D is said to be a deformation retract of the space X. Then D is a deformation retract of X, provided that there exists a continuous function. See, there must exist a continuous function. That function is H. And this function H is defined from the product space X cross I2 the space X. It is defined from X cross I to X, and also it must satisfy the condition. This is the set of conditions that must be satisfied by this function, which is going to be called the deformation retraction, and that is h of x, comma 0. See, x comma 0 is a point of the space X cross I. So h of x0, x comma x0. So by avoiding for convenience, we just avoid the comma. So x comma h x0 equal to x, and x h x1 will be giving us the subspace D. H x1 equal will be given means it will be a member of the subspace D. So h x1 is a member of the subspace D. And this happens for all x belonging to x, and hyt equal to y. See, hy comma t equal to y, where y belongs to D for any y belonging to D, and any t belonging to which belongs to I. The function, this continuous function h can be called the deformation retraction. It's called deformation retraction, since for each y in D, it has the property that for each point y in D, hyt is fixed. That means hyt equal to y. So hyt has the constant value y. See, as t varies from, so it has the constant value y. Hyt has the constant value y as t varies from 0 to 1. So the variation of t in the interval 0 1 will not be affected the value of hyt whenever y belongs to the subspace D. And so we say that due to this reason we can say that h actually then fixes the points of D. Also we can say that D stay fixed throughout the deformation retraction. We want to discuss some examples. The first example, it's a special case of a more general situation that we will be discussing after this. So consider the annulus. Here we have the annulus. This annulus has the two boundaries. It has two boundaries, the outer boundary and the inner boundary. Its outer boundary is given by the circle x square plus x1 square plus x2 square. See, x1 and x2 are the coordinates, first and second coordinates. x1 square plus x2 square equal to 4, and the inner boundary in inner circle is given by x1 square plus x2 square equal to 1. So the radius of the circle, the smaller circle has radius 1 and the outer circle has radius 2. So the space can be written as A equal to the set of all those points x1 comma x2 which belong to R2, satisfying the condition 1 less than or equal to x1 square plus x2 square less than or equal to 4. And we define the function h. Actually we want that function h defined from A cross I to A. The function h is defined from A cross I to A by h of x comma t equal to 1 minus t into x plus t into x divided by norm of x. 1 minus t into x plus t into x divided by norm of x, where the points x comma t belongs to the space, product space A cross I. Then you can verify that hx0 equal to x by simply substituting the value t equal to 0 in this expression. You can simplify it to obtain that hx0 equal to x. Similarly, hx1 equal to x divided by norm of x, but by taking its norm, when you take the norm of this quantity, norm of h of x comma 1, you get that it is norm of x divided by norm of x equal to 1. And that says that this point, all the points belonging to hx1 as x varies, and when the second coordinate is kept fixed, it belongs to the unit circle S1, that is the inner circle. The inner circle S1, it belongs to the inner circle S1. Yeah, it's in this all the elements that we are going to get here, that is x comma 1. All those points are members of S1. And then the third condition, h of yt equal to h of yt equal to 1 minus t into y plus t into y divided by norm of y. Since norm of y equal to 1, it's because you know that y belongs to the inner circle. Here we are going to consider, here we are taking D, the subspace, as x1 square plus x2 square equal to 1. That is the inner circle. For that inner circle, those points belong to that inner circle, its norm value. If y belongs to that inner circle, then norm of y equal to 1. Therefore, that can be substituted here. That value can be substituted here, and then you can simplify it to obtain that the answer equal to y. See, 1 minus t into y plus t into y. When norm of y equal to 1 substituted, then we get y, and that means y belongs to S1. And therefore H is a deformation retraction. Why? Because H satisfies all the conditions of a function to become a deformation retraction, and so it's a deformation retraction from the given space A to its subspace S1 here. So here D equal to S1. But see, as I have mentioned in the beginning, see, we have a general situation, a general case as an example. See here, for that we consider A equal to x1 x2 in R2, such that A square less than or equal to x1 square plus x2 square less than or equal to b square. So it's also an annulus. It's an annulus, but its outer boundary is determined by the circle x1 square plus x2 square equal to b square, and the inner boundary is determined by x1 square plus x2 square is equal to a square. And you are going to take D, the subspace D equal to the set x1 x2 belonging to R2, such that x1 square plus x2 square equal to c square. See, it's the circle which comes between. It's an inner circle which comes between the smaller circle and the bigger circle. So C satisfies the condition A less than or equal to C less than or equal to B. See, to say that, to show that it is a deformation retraction, we want the function. That function is given here h of x comma t equal to 1 minus t into x plus t into c into x divided by norm of x. So 1 minus t into x plus t c x by norm of x. See, we are you can verify that conditions, the first two conditions, all the three conditions you can verify. So it's left as an exercise for this case. Now another example and come discussion. In this discussion we are going to recall a concept that we have studied earlier, a contractible space and contraction. That's the concept of contraction. what is meant by the contractible space? When we say that a space X is contractible, a space X is contractible to a point X naught which is present in the same space if and only if the single point subspace X naught. See, if and only if there exists a point, a function, and that continuously reduces that space to shrinks that space to that single point X naught. So, but there is a definition for mathematical definition for this contraction. But you can now think about that concept in the setting of deformation retract. See, when you compare these contractible spaces with the deformation, this current definition, you can see that in the you can apply the deformation retraction. You can apply a deformation retraction on the space X, considering the single point, as the single point singleton set, which can be treated as the subspace of X. So the single point subspace. We can consider the single point subspace D equal to a set of X naught. D equal to set of X naught, set X naught, where X naught is the point to which the space X can be contracted. And then you can easily define a deformation retraction function that can reduce this deform the space X easily to that single point subspace X naught. And thus any point of using this concept, applying this concept, we can see that any point of Rn, consider for example R1, that's the simplest case. R1 is the real line. So any point on R1 can be treated as as the single point to which it can be that our entire space can be deformed. It can be deformed. So we can say that R can be deformed to the single point on any point on R. And then R2 can also be deformed to a point which is present on R2. See, R2 can also be reduced. So R2. Thus, in applying this in the general setting, see, we can say that Rn can be, that is the Euclidean n-dimensional space. Euclidean n-dimensional space can be deformed to a single point which is present present in Rn. So any point of any point of Rn is then therefore it can act as the deformation retract of Rn. And then any point of now we can consider a special case of this situation, that is we can take a subspace of Rn, that is Bn. Bn is the subspace of Rn, that is the n ball, the n ball Bn. Bn is the n ball, n-dimensional ball. N ball means n-dimensional ball. So n-dimensional ball can be deformed to into any point which is present in that n ball. So any point of the n cube in a similar way. In a similar way we can say that the n cube in I to the power of n, I raised to n, the n cube in can also be deformed to a single point in the same space. So in can be, as in essence, we can say that in can be deformed to any point present in that space, and Bn can be deformed to any point present in that space. So in a similar way, so in the most general situation, Rn can be deformed to a point present in that space. Okay, that's about the deformation retraction and then the deformation retract of topological spaces. So thank you.